Well, hello everybody. My name's Derek Nelson. I'm one of the core developers of a database product called PipelineDB, and I'm going to talk to you a little bit about what that means today. So obviously the first question is, what is PipelineDB? At a high level, it's a database product that allows you to run continuous SQL queries on streaming data. As these continuous queries are running, they incrementally store the results of these continuous computations in tables that you could query just like regular Postgres tables. So typically the best way to think about this idea is a continuous view is essentially a very high throughput, real-time, incrementally updated, materialized view. And one of the unique things about it is that all the data that's used to build these continuous views doesn't actually have to be stored in the database. So once these continuous views have updated with the information that they've read, that data can be discarded forever. And so what that means is that they really allow you to break the dependence between the size and the complexity of the database and how it grows. That can be completely independent of how much data you've pushed through the system, which is nice. And it's, of course, GPL v3, so it's open source. You can check out our GitHub page and use it anytime you want. So to give you something to hang that on, since we all know SQL here, here's an example, excuse me, here's an example of basically a canonical continuous view, just selecting X, count star, group by X, and here's a more complicated one. We support basically the full range of PostgreSQL, which is really nice. We don't have our own domain-specific stream processing language or anything like that. So really any query you could run on a Postgres table, you can run on these infinite streams. So we try to maintain as much compatibility as possible. So the next obvious question is, why did we build this in the first place? And we have a background in the advertising technology industry, which is a very data-intensive industry, and we were early adopters, early users of a lot of the cutting-edge open source big data stream processing technology. And a lot of those technologies were really complicated, a little bit more complicated than we want. But fundamentally, we built this data always originates as streams. But it turns out, as I was saying, it's very hard to actually process it in the same way that it's produced. It's much easier to just dump a bunch of streaming data or stream a bunch of data into a large database and then run queries on it later. It turns out it's actually very difficult to process continuously. And so we had to develop a lot of complex technologies and architectures that allowed us to do that. And what we found was that a lot of the tools, they were, as I said, too complicated. They're disparate, so we had to use a lot of different systems and integrate them with each other, which required a lot of operational knowledge and overhead just to run these sort of disparate systems that solve these stream processing needs. So what we set out to do is build PipelineDB, which is a much more unified approach, and it allows us to run continuous queries without having to write any actual application code. A lot of stream processing technology out there today gives you basically the primitives to develop streaming applications with code, and we wanted to do everything with a query language because a lot of the queries we were essentially running on streams fit really, really nicely into the domain of SQL. We're essentially counting things, running analytical queries, and things like that. We also wanted something that was highly compatible. So we actually don't have our own proprietary API, client libraries. PipelineDB looks exactly like a Postgres database, so it's completely compatible with any of the client libraries that are already out there being used. Which comes to the next point. What does this have to do with PostgreSQL in the first place? Why am I talking about it here in Dallas this morning? And PipelineDB is actually a PostgreSQL fork. We wanted to choose a really mature, robust database to build our product in and around. It obviously takes a very long time to build a database as rock solid as Postgres, so we started there instead of starting from scratch, which made it a lot easier and makes our product pretty stable. And it's also, Postgres is also ubiquitous. As I said before, we wanted something that's highly compatible, easy for people to use, doesn't require any sort of proprietary knowledge or anything like that. And the other reason, which is nice, is it has really, really good JSON support, as we all know, which is really nice to have. And the license, of course, it's extremely liberal, which allows us to do anything we want with it. And as I said, the license of our product is actually GPL. So that's sort of a high-level overview of what we're doing and what our motivation was behind it. So we can talk a little bit about how the product actually works now. So let's start with a query similar to the one I mentioned before. Select count star from stream. This is just a really simple query and will hopefully allow us to sort of understand how these continuous queries are working under the hood. So there are a couple different layers to the whole flow of when information is produced to when it is consumed by a continuous view. So it starts with a writer, and writing into a PipelineDB stream is the same as a SQL insert. You can also use copy. So any way you can get data into a table, you can actually get into PipelineDB by a PipelineDB stream with the exact same syntax. So the next stage is the worker process, what we call the worker process. And this process is reading from a stream as fast as possible, and it's repeatedly executing this continuous query plan on what we call micro batches of data. So here, if the query is count star from stream, obviously the worker here generates a 2 when it sees 2 rows. And the final process is what we call the combiner process. And this is where most of the interesting work happens. The worker query and the combiner query are both variants of the root query, count star from stream here. And you see the combiner query is actually summing whatever's coming out of the worker with whatever is on disk. And that's how these things are incrementally updated over time. That's how it's merged in. And so everything the combiner writes out to the actual table, what we call a materialization table, and it just writes stuff out as fast as possible, these updates. So when I say worker and combiner, the way that these are actually working under the hood are we use the background worker infrastructure that ships with Postgres. So we leverage that pretty heavily. Any number of workers are running and any number of combiners are running in parallel as background workers. So we leverage that infrastructure, which is really nice. And it's a pretty easy to use API, which makes it easy for us. So digging in a little bit more to the worker, we've added a couple of query nodes to the planner and analyzer in those stages that help us conceptualize running these queries on actual streams. So node stream scan is the main node that the worker uses. It's just a different node in the query tree that reads from a stream as fast as possible. So whenever those writers are doing the inserts, those get put into a buffer in memory, and the stream scan node essentially reads from that buffer as fast as possible and drains it as fast as possible. So you can essentially think of a stream scan as just like a normal table scan, except it runs forever. It keeps going. And as I said, that runs on micro batches. So every 1,000, you might want to run this continuous plan. Every 1,000 new events that come in, or every 10,000, it's a configurable parameter, and there are trade-offs to changing it in various ways. So that's how the stream scan node works. It just reads batches from the stream scan buffer. So the other process, the more interesting process, as I said, is the combiner, and this is running as a background worker, and it's got a couple of unique things in terms of how it works. So this combine function we have, this is actually a special aggregate that PipelineDB has that can actually take 2 aggregate results, combine them into one, as if the final output was the same as all the original inputs having gone through it. So obviously things like combining an average, it's not just a matter of taking the average of the averages. You have to take the weight into account, and combine can do that for us automatically. So that's essentially the function that is used on the combiner. And we actually store, this is what an actual materialization table looks like. Under the hood, this is what a continuous view looks like. So here's the query, select average and count from stream. We're not actually storing the average in the table itself. We're storing what's called the transition state internally in Postgres. So here you have the transition state of certain types of average, or you keep you see the count here, the total of elements that you've read through, and then the next one is the square of the total, which is used for some other operations. And then count, you see, it doesn't need any special transition state, so we can just store the number there. And so, as I said, since we don't actually store the value of the average, we have to compute that on the fly, and we do that with putting an overlay view over the materialization table that looks something like this. So we call the finalize function, which actually runs the average on that transition state, and then send the result to the client. And that the VMREL there, you see, that's the actual materialization table that these continuous views are using to update. Another thing that is challenging with the combiner is we have to pick out the groups on disk that need to be updated with the incoming result that is given. And we had a bunch of challenges with this early on. We index these materialization tables based on the groups so that we can look up the groups to update as fast as possible. And in the beginning, it was really hard because obviously the best way to choose an index is to use the most selective column. But since we're essentially creating these indexes automatically under the covers, under the hood, so it's not easy for us to wisely choose the correct column to index on. So we had a lot of problems there by choosing the wrong columns, making dumb decisions about that type of stuff. And so what we do now is we actually take a hash of the group. And what this does for us is it maximizes the cardinality of the underlying index, so that when we're looking at what groups we need to pull off disk, we scan as few rows of the index as possible. If there are a lot of similar groups, this is a problem we had. If there are a lot of similar groups in the index, you're going to do a lot of wasted scanning, which really slowed down this performance critical path. And so hashing the group and indexing on the hash value probably sped it up by a factor of 10, about an order of magnitude. So this is the best way we've found to automatically select an index column for automatically when the user creates this. So you could essentially think of this as, and this works in general for Postgres. If you do this, if you want to index a table using this exact same scheme, it's pretty helpful to index on the hash instead of actual columns. It typically makes things pretty faster. So essentially what this is it's a hash index, but it uses the underlying B-tree implementation. The hash index implementation we didn't find sufficient for our uses yet. The one that ships with Postgres, the B-tree is a lot more mature, and there are a few quirks surrounding the hash index, as I'm sure a few of you know, that made it a little bit harder for us to choose to use. So this is essentially a hash index with a B-tree underlying it. And so this is one of the questions that we get asked a lot. So that's sort of a high-level overview of how things work. One of the things we get asked a lot is why wouldn't we make this an extension? And that's something we really do want to do, but we've made a lot of changes fairly deep in the planner, in the analyzer, in the parser that make it really hard for us to factor this out as a completely separate extension. So we essentially need more hooks. And this is something we're trying to work with the Postgres community on to help out there. A lot of people want more hooks in general to make the extension API a little bit richer. So that's something that we're looking to do moving forward. Because about probably 90% of our code is completely separate from the Postgres core, so it's pretty feasible for us to ship it as an extension, which, as I said, a lot of people want. So that's the end goal, is to eventually have all of this factored out as an extension. So that's at a high level how it works. I wanted to leave a little bit of time if anyone has any questions about how it works or anything like that. Yeah.
Yeah, you showed insert into stream.
Uh-huh.
Is there a special kind of table, special structure that you have to put data to, or can you just hook this onto normal tables?
Yeah, that's a good question. So he asked if when you're inserting into a stream, how is the stream actually constructed? So there are two ways. So you can actually do create stream. We call that a static stream. So you predefine the types, the input types of the stream. The syntax is the same as creating a table. We also have inferred streams. So you can actually add casting to the continuous view definition to tell our planner what types to use, and then you can just actually start writing to a stream that you never created with create stream. So It can happen implicitly or explicitly. Yeah.
All your examples just said stream, but I assume you can create different streams with different names and have, for instance, multiple views off the same stream and a completely separate stream, which is pushing to other views. Yes.
Exactly. So yeah, it's a stream is essentially internally we consider it just like any other relation, really. So you can have any number of streams, any number of continuous views, completely separate from each other. The worker processes and the combiner processes, they process all the continuous views at once. So it's not every continuous view doesn't get its own group of processes, but effectively, yeah, you can have as many as you'd like.
And you can have as many continuous views on the stream as you want.
Correct. Yeah, exactly. So many different continuous views can be reading from the same stream. Yep. Any other questions? Yep.
Like a segment size, or what is the buffer that of a stream that if somebody misses out, how far back can they go with that?
Yeah. So it's actually his question was how far back in time can you go with a stream? And it actually gets, as soon as the continuous view is updated, the data is gone forever. So the materialization table, the continuous view is transactionally updated, and as soon as that transaction completes, the stream is just discarded, essentially. You'd be able to write continuous views in such a way that data does actually get saved somehow, but by default, nothing happens under the hood in terms of saving that. Yep.
In terms of backup, I mean, I assume you're going through all the normal wall stuff and start backup, stop backup, so all that stuff will work. So if I want to back up a PipelineDB, I can back it up in exactly the same way I would back up a Postgres database.
Yes, exactly, because everything's just stored in tables internally. So yeah, that's correct.
Okay.
Yep.
Question about from the consumer end.
Mm-hmm.
So you can have multiple processes looking at a stream, right?
Correct.
So how does one process know what's new to it versus this other process has maybe more up to date, only needs to see the last row, this one hadn't seen the last 5?
Mm-hmm. So her question was, sorry, go ahead.
Just how does that work?
Yeah, so her question was how do these different continuous views know which data they still need to read, because they could be reading at different speeds or something like that. Each data point that comes into a stream gets tagged with a bitmap, and each position in the bitmap represents one continuous view that needs to read it. And as soon as a continuous view has read it, it flips the bit to 1. And as soon as they're all 1, the data can be thrown away. Does that answer your question?
No, I'm thinking more like from web apps. It's got multiple processes, connections to the database.
Mm-hmm.
All may be looking at the same stream, but they're not all at the same point in the stream.
So
I know this process, which data to give it.
So in terms of clients, these things just look like regular tables to a client. So if a web application was looking at a continuous view or something, it's just the same as like selecting from a table. So we don't stream data down to clients yet. We call that push, and we'll eventually have that functionality. But right now, you just stream data in. There's no data that's streamed out to clients, though. So it's just regular table consumption with selects. Yeah.
What is your mechanism to populate these views, these continuous views that you call? What mechanism that does it use to get refreshed from these streams? But is there a time-based thing, or is it a manual kickoff thing?
So these background processes will start as soon as the database starts up. The background workers are launched, so they update as soon as new data comes in. If no new data is coming in, these processes will go to sleep. They'll essentially sleep.
So it's instant as it happens.
Right, it's instantaneous. So as new data comes in, they get woken up, and then they'll read as fast as possible.
So is there a configurable way to say, do it every 5 minutes, or don't do it for an hour or so on?
No, currently there's not. No. Good question. Any other questions? Yep.
Does this have to be on your master, or could you set up a slave that somehow does this?
So this works with standard Postgres replication. So we don't do anything special with replication. You could have one box doing all the reading and then just replicating out to another slave without the continuous queries running. You could do that. Is that what you meant?
I was thinking the reverse, where we would have a master. I was thinking the reverse, but that's not.
Okay. Yep.
From the standpoint of, did you guys change the catalog numbers and control numbers sources and stuff like that for this version. In other words, if there's a process that's actually looking at the system and reading PG control, is it going to be able to tell this is not Postgres, or is it going to look exactly like Postgres 9.4 or whatever version you've worked from?
Yeah, so we actually, the catalog version is, it's the exact same as Postgres 9.4.4. We've added a few of our own catalog tables, but we haven't changed any of the existing built-in IDs. We just go from, we have our own numbers.
Okay, so it will look just like 9.4 from that perspective. So
Exactly.
It'll be identified as a 9.4 system and treated as such.
Correct.
Okay.
Yep.
Cool.
Any other questions? Yeah.
Is are the streams themselves flaw logged and whatnot, so that if your stream backs up for whatever reason and then you have to do a failover, that data will still be maintained?
Yeah, so his question was, is the stream data logged to the wall just like other data? And the answer is no, it's not. So there's as I mentioned, there's a buffer, in-memory buffer that the streaming data goes into, and that's essentially the unit of loss, potential data loss. If the stream buffer is full and there's a crash and nothing reads it, that data will essentially be lost. And right now I think it defaults to a couple 100 megs, 128 megs, or something like that, but that's configurable. Yep. Potentially it could, yeah. We do have a setting that essentially makes stream insertions what we call synchronous, so they won't be acknowledged as successful until the commit in the continuous view has actually happened, but we don't recommend using that setting because you lose a ton of speed. Any other questions? Yeah.
Any other special settings that y'all recommend to optimize the performance?
Yeah, so our defaults are slightly different than standard Postgres defaults. In particular, we've made the auto vacuumer a little bit more aggressive because these tables are being updated very, very quickly. And so we had some issues with the default auto vacuumer configuration, and a couple other things that we've changed the defaults. Yeah. Anybody else? Okay. Well, thank you all for coming.